I'm Professor Q. So glad to be with you. And I have a quick special guest named Rocky too. Say hi, Rocky. Well, he and I are here to be able to talk about something that bends. There's many things that bend. Can you think of some things at this point? Well, my question is, what is the bending of light? Is that an air bender? Of course not. But what it is also called in the scientific terms, the term refraction. Everyone say that. You ready? Refraction. That's right. Now, I would like to discuss a little bit about the English part of science. What word can you find in the term refraction? Did I hear you correctly? I think I did. Can we say the word fraction? That's right. What does fraction mean? Well, in mathematics, it's talking about a proportion, a part of. So today we're going to be discussing how light behaves when it's in different mediums, such as in a vacuum, or in a solid, or in a liquid form, just a bit. So, what I would like to discuss with you today is a little bit about prisms. Why is prism so important? Well, because prisms react differently in how light behaves. Right, Rocky? Exactly. So, let's take a look here at this point. And as I have this prism, what do you think will happen when I shine the line up above the prism? Well, in my last video, in episode 2, we discussed about reflection and how this looks like it's reflected. However, if I were to also put the light in this direction, you might be able to see that there's very clearly some type of coloration that's occurring. Well, why is that happening? What do you think? At this time, go ahead and pause the video and write down in your STEM journal why you think we're able to see different colors of light when we put the light rays through the prism. So, what did you infer about why the light was different when it went through the prism versus just a normal type of light overall? Well, I think you're right, because this prism is actually a solid. And when light goes through a solid, now the question is this solid transparent? Is it translucent, or is it opaque? Correct. This is transparent because you can see through it. So this light, even go through a solid, will start to actually refract or bend. And when that light ray bends, you have a scattering of rays, therefore breaking out into the different colors of the electromagnetic spectrum. Now, what do these colorations resemble that of? In fact, it would be a rainbow. And rainbows use both areas of both refraction and reflection. When a light ray actually connects and interacts with a raindrop, it will bounce off of that raindrop, and then that light is scattered throughout. So we get to see Roy G. Biv in the sky. So I have a trivia question for you. Are rainbows circles? What do you think? Have you ever seen a rainbow as a circle? Well, actually, rainbows are in nature circles, but why can't we see them as such? Did you say it's because of the horizon? Correct, because that horizon splits that circle so we can only see the top half of it. Isn't that exciting news? So I challenge you, the next time you see a rainbow, try to find the end, because really, is there one at all? Oh, this is so much fun. Well, now I'd like to also discuss with you a little bit more of interaction. So I have this wonderful glass jar that's here, and I'd like for you to predict, what do you think will happen when I place this pencil in the glass jar? Go ahead and make your prediction now. Okay, so are we ready to go ahead and explore? Here we go. Observe very carefully what happens to this pencil. Now we have to get eye level, so let's do that. Oh my goodness, what do you see? What has happened to that pencil? Well, let's make some great observations. So as you notice that the top part of this pencil is as it was when I first put it into the jar of water. However, the very bottom part, first of all, it seems like it got bigger, puffier, right? And what else can you see? Well, let's take a look at this flat plane at the point at which the pencil inserted into the water. It looks like it's broken. Oh my, who broke my pencil? Well, actually, why is that so? Well, that is actually a property of refraction once again. Okay, well, let's move on, and then at the end, we'll have a conclusion and debrief to see what occurred all together. Okay, so let's go on and elaborate a little bit more if we can, and explore with the types of other experiments regarding refraction. So, as you see, I have small arrows. Which direction are the arrows pointing? Correct. They're pointing they're going towards the right-hand side. And so by doing that, though, I want us to carefully observe what happens when I place these arrows behind the water. Okay? What do you think? Go ahead at this time and make your prediction. All right, here we go. What do you see? What do you see? Are the arrows pointing the same direction? Or are they pointing a different direction? You're right, they're going the opposite direction. What happened? Oh, this is the science behind the science of refraction. Well, at this point, what do we know about water? Well, we know that it's clear and we know that it's transparent, such like that of the prism, correct? Okay, so we have some commonalities so far. Well, I have one more experiment for us to see, and I think we have another guest. Hello, Twinkles. How are you today? Are you doing well? I know. It's so good to see you too. Thank you for joining us. Okay, so I love these science sayings. It says, think like a proton, be positive. Sometimes you just got to be a little fun and enjoy yourself. So exactly, we have to do that. We have to think positive. Now, what I'd like for us to view is that, well, what type of dish do I have here at this point? Correct, it's a Petri dish. And there's some types of materials in this Petri dish. Can you see what that would look like? Yes, well, and one observation is that they're spheres, like round little balls, okay? And you can see through them, absolutely. So this is evidence like that of our jar and the water being transparent, as well as a prism being transparent too. So my question to you is, in your STEM journal, make a prediction of what do you think will happen when I put think like a proton, stay positive, underneath my Petri dish. Okay, let's think positive like a proton, shall we? And let's make your observations. I know you have your prediction. Here we go. Ooh, what happened there? Can you see the image at all? I see a little bit of the writing, but not to the extent that I could actually read it. What is happening there? Well, now I have another prediction for you to make. What do you think would happen if I were to pour some water into the Petri dish? Go ahead and write that down in your STEM journal. Okay, well, I'm glad to hear of different types of inferences that you're having regarding what would happen when water would be poured into this Petri dish. So before I start, a little bit of science quizzery of what particular type of science equipment am I holding here? No, it's not a beaker, because a beaker has like a little beak at the end of the container. Now, it does have the beginning of a cylinder. It's a flask. See the main difference between a graduated cylinder and a flask? Okay, fantastic. So let's go ahead and start to pour and make the observations. Can you see anything yet? Is anything happening? Let's pour a little bit more. What's happening? What are your observations? Oh my goodness, I'm starting to see the saying, aren't you? Wow! Think like a proton and be positive. I can read the whole saying. And I can even, it doesn't even look like there's anything in there, really. So why is it? What is the commonality between all of these three things? Well, let's go over here and have a quick conversation about refraction. So, as you see, this would be our plane, our level plane, and this would be the air, and we could actually say that this would be water on the bottom. So what happens is when the light ray is traveling 186,282 miles per second in the air, it's going really quick, really fast. It has really hardly anything to slow it down. So, but when it starts to hit a liquid or a solid, it will immediately slow down and scatter around. Let's say it will slow down and scatter around. Okay? So when that light ray hits a solid or liquid, what is it going to do? It's going to slow down and scatter around. It's going to bend. It's going to bend. So that's what happens here is you see your arrow, light arrow, and hits the solid liquid area and it will start to bend. So we have the angle of incidence. I think you've heard of that before when we discussed reflection. And now we have the angle of refraction in this sense for the law of refraction. And this is our normal line to be able to identify where that point, focal point is of insertion of the light ray. So having this understanding now, having that opportunity, let's briefly discuss what happened overall. So when I place my pencil into the jar, this clear water acts as a magnifier. And as it magnifies, it magnified the very bottom. And the point at which the light that we are visually seeing through our eyes to see is actually causing us to view that there is the actual bend of light. Now, is this pencil actually bending? No, it is not. It's what we are visually observing, how light is behaving when it actually has a light wave. Because the light ray goes to the water, it goes through the glass, and then it will come back out the glass, and then back to our eye. And that's how we see. And the same instance here as well. What happens is that water then again acts as a magnifier, but what occurs is that when light bends, it can also transform the image in the opposite direction. That's why we see opposite rays from what they normally were when they were first drawn. Now, okay, Professor Q, but what about staying positive like a proton? What happened there? Well, if you remember previously that there's actually little spaces, I call them pore spaces, just like that. You have pores in your skin and you have pore spaces. And so what happened is that the water filled up the little pore spaces to behave much like that here of the water in the jar. So that when the light interacted with the water and the solid spheres, there was a lot of fraction and bending of light. Isn't that so neat? I think so too. Don't you? So before we go today, just to help remember the difference between reflection and refraction, remember that refraction means to bend. Well, just like I had my little dance of reflection, I have a refraction dance as well. So our right hand is going to be the angle of incidence, and the left hand is going to be the angle of refraction. And so, but we have to bend this time. So we have the angle of incidence. We're going to pretend that we're going to hit this table and move on and bend as the angle of refraction. Are you ready? One more time. Angle of incidence, angle of refraction. Angle of incidence, angle of refraction. All right, we got the music going on. Okay, more like disco dancing per se. Wonderful. In everyday life. So it's in your glasses. What about telescopes and the astronomy, looking at the stars? Also, if you happen to be in the desert, it's what about those mirages? Oh my. Be careful about those, okay? So it's wonderful to be able to be with you today. And remember this, be strong and good, better, best. Never let it rest till the good gets better and the better gets best. Telescopes. And what about those mirages in those deserts? Oh my. So think about and observe your natural surroundings because refraction is everywhere around you. So with that being said,